Gamelin puts forth. This book, Gamelin, was recommended to me by a guy who his career work is analytical number theory. All right, so like he is not just an analyst, he's an analyst who actually computes real things. And to him, the approach of Gamelin is excellent. But if you read reviews of this book, you'll see there's a cadre of critics who are like, it's just very unrigorous, because they want to see epsilons and n's, and you know, there's places where he's a little bit eh. But anyway, so there's that theorem. I know we got a football game to go to, so let me wrap this up here. So next up, definition: a sequence of holomorphic function converges normally to an analytic function f on D, or you could say holomorphic function f on D, if it converges uniformly to f on each closed disk contained in D. I mentioned this about 5 minutes ago, but there's the definition written out in all its glory. And theorem 8.218, suppose that f is a sequence of holomorphic functions on a domain D that converges normally on D to the holomorphic function f, then for each m greater than or equal to 1, the sequence of mth derivatives converges normally to the mth derivative of the limit function on D. This is all wonderful. The reason this is wonderful is because you should understand that this is paving the way for us to prove everything about power series effortlessly. Because what is a power series? It is a sequence, well, it's a limit of a sequence of partial sums, right? But what are the partial sums? What are we summing? Power functions. Are power functions continuous? Yeah, they're continuous. So are they uniformly continuous? Well, given the proper context, sure. Oh, here's a fun quote that no one cares about. So this brings us back to power series. So let us put into practice everything we've just developed. All right, let's apply this beast. So we have a power series. We talked about these before. They are just like calculus 2, but now you got complex numbers and complex power functions, right? What's new here is the way the convergence is dealt with, as like the material I was sampling from to talk to you guys about convergence, like our proof of the ratio test and so forth. If you compare it to the proof that's in my notes here, it looks a little bit different, because the central what's the word? This is the fulcrum on which everything else kind of bends. This Abel's convergence lemma. Suppose for a power series that that there are positive real numbers, modulus of the coefficients of the power series times s to the k, which is less than or equal to m for all k. All right. Then this power series is normally convergent on the open disk with radius s, centered at 0. The proof is right here. Consider R to be between 0 and s. Let Q be the ratio of R over s, which is necessarily less than 1. And then if we pick Z in this open disk here, by our assumption we have the modulus of a sub k z to the k is less than or equal to modulus of a times r to the k, which if we divide and multiply by s to the k, we got that. So then we have a to the k, s to the k times that, which is, we're assuming that this is less than m, right, by assumption here. So we have mq to the k, but what is mq to the k? Well, you've got m, which is a fixed positive number. Q is a ratio less than 1. This, my friends, is a majorant. It's a majorant for the series with these terms, because this, when you sum it up, is geometric. It converges. Consequently, we have uniform convergence, and hence by Weierstrass's m-test, we have convergence on you know, this r radius r subdisk, but that was arbitrary, so that gives us the normal convergence since it was for an arbitrary closed subdisk. That's pretty cool. And a corollary to that, one of your problems is to prove that and the corollary. I remember that. The corollary is if the series converges at one non-zero z, all right, then it converges normally in the open disk with radius, the modulus of that convergence point. In other words, if you find one point out from the center of a power series which converges, everything closer than that point must also converge. Not just that, it has to converge uniformly. And we know what that means now. Well, we're learning. Yep.
The modulus of everything goes to that, or like everything on the line?
Everything, all point, I mean, like it's all points. So this, if a point distance 3 from the center of a power series converges, then the open disk of radius 3 centered at the center of the power series, all of those points are points for which the series converges. And not just that, it's a uniform convergence. So anyway, here's the proof of the corollary. If we have convergence at one point, then we satisfy Abel's criteria, and consequently, well, rather, if we have one point of convergence, that means that by the nth, well, in this case, the kth term test, it goes to 0. But if it goes to 0, a sequence of positive terms which goes to 0 is necessarily bounded. And if it's bounded, well, that bound gives you, satisfies the Abel criteria, I believe. And so there exists, I mean, well, anyway, more to the point, it satisfies Abel's criteria, and then we just apply the previous lemma, and we get the convergence that we want. Okay, so therefore, we can define a radius of convergence simply by, well, the radius of convergence is what? It's the R for which you have convergence for less than that R, and you have divergence for greater than that R. And in the case the series converges everywhere, we say R is infinity. In the case the series only converges at the center, we say R equal to 0. And the theorem which follows says that essentially that R exists. All right. There is a R such that it's either 0, finite, or infinity, such that this power series converges normally within the radius of convergence. You just construct R to be the supremum of that right there, and that supremums exist, and then it's Abel's convergence lemma. So I won't bore you with these examples here. We kind of talked about these sort of things before. This is just returning to ratio test or geometric series test, like, that kind of thing. Divergence by the nth term test, great, lovely, who cares? I mean, I guess I care. This theorem I care more about, though. If we have a power series with radius convergence R greater than 0, then the function defined by the power series is holomorphic. Why? Because it is a series of holomorphic functions. Because power functions are holomorphic. Therefore, a series of power functions is holomorphic. Therefore, I can differentiate term by term, and also those functions are holomorphic. Like the limit, here I'm using the derivative of the limit is the limit of the derivatives for the sequence of partial sums, that theorem. See, I don't have to, that horrible calculation I did in class to prove that the term by term derivative of a power series was itself complex differentiable. That was a hard calculation, right? It took me like 20 minutes to kind of do it. And even at the end of that, what did I do? I switched the order of integration and a limit. If you watched me, I did that. Or differentiation and a limit, I guess. And that doesn't happen here. Like, this is a complete coherent proof that you can do term by term calculus on power series. That's what these arguments prove. So here's some term by term calculus in power series, but we can talk more about that. We will talk much more about power series computation probably like next time. This right here we have talked about before. This is the, what is this? If a sub k over a k plus 1 has limit, it's either finite, infinity, and the limit's the radius of convergence. That's what? It's the ratio test is what that is. It's the radius of convergence version of the ratio test, which isn't generally true. It's only good for a series without 0 terms. Here is our beloved Cauchy-Hadamard test, which is also not proved in these notes. And still, I would not require of you, relax. And that brings us to section 8.4, which is probably where I'll pick up next time. Let me tell you what we're going to do. So next time, I'm going to explain to you that when you put all this stuff together, we're able to argue that the exponential, the sine, the cosh, the sinh, all of these functions that we've defined by power series, right? When we look at the theory and we understand what's all going on here, we'll understand that because all of those functions are, well, let me not give it the whole argument, but basically all of those functions have to be what they are if they're going to restrict to the ordinary exponential, the ordinary sine, the ordinary cosh, the ordinary sinh. Like, there is only one possible complex function that restricts back to our regular real functions that we already know. In other words, the definition of the complex exponential that I gave you early in the course, it cannot be anything but that. So we'll discover this sort of extension theorem that says basically holomorphic extensions are in some sense unique in a context. There's a context for that uniqueness. Now that naturally leads then to the discussion of analytic continuation, which is where that uniqueness gets kind of twisted a bit because, well, that's a different context. So anyway, thank you for showing up today. I do appreciate it.